All right, point X is at 100 Kelvin, so we know how many moles there are. The work done for the adiabatic process cross country, XC, right? This guy here is 1250, and they have to tell you that, but actually they don't. Okay, I'll do a separate video where I show you how to do that. Okay, so what is the pressure at point C? Right, so we know the initial pressure and the initial volume. Notice that these are times 10 to the fifth, and that's 10 to the minus third, right? Okay. So we can find it. And this, we're going to use the famous PV to the 5/3 is PV to the 5/3. So remember that in an adiabatic process, we can't just say PV equals PV because the temperature changes. It changes with the volume, and that's why the volume is raised to a number bigger than 1. Okay, and somebody has to tell us that, right? Deriving that is maybe difficult, right? Okay, so let's find the pressure at point C. The pressure at point C, let's see. So P1 is, I'm going to start this. This is going to be P1 V1. This will be P2 V2, right? 5/3, 5/3, right? Okay, so the pressure, we've got 8 E5, and by that I mean 8 times 10 to the fifth, right? And then 2E minus 3 raised to the 5/3. That's going to equal, and then what's our, I guess we're finding the pressure, right? So pressure 2 times, and then our volume is 6E minus 3. Raise that to the 5/3, right? So P2 is going to be this divided by that, right? So I'm going to go 8 E5 times 2 e to the minus 3 raised to the 5 divided by 3, hit the right arrow, divided by 6 e minus 3 raised to the 5 divided by 3. I'm hitting the right arrow just because I feel like I should, but it doesn't matter. Okay, so that pressure is 128,199, right? Pascals, which kind of looks right. And if you look at that, right? Because I actually did this. I actually made a spreadsheet that I actually did this. I didn't just take auto shapes and bend them. Okay, so if you go there, that is 1.282 times 10 to the fifth pascals. And we really don't have 4 sig figs. I don't know. I'm so proud of that number that I feel like I should, over-represent its accuracy. Okay. So what is the temperature at point C? This is complicated. But not really. Let's use the combined gas law. So PV over T is equal to PV over T. And this is situation 1, that's situation 2. Right, so T2 is equal to P2 V2 times T1 over P1 V1. All right, there we go, T2. Is that right? Did I do that right? I put this guy in the numerator. I multiply both sides by the reciprocal of this. I feel like that's right. Okay, so T2 is equal to pressure 2, volume 2. Okay, so here's pressure 2. 1.282 E5, volume 2 is 6 E minus 3. Right, our first temperature is 100. Right, this is 100 kelvins here. Okay, and then pressure 1 is 85. Volume 1 is 2E minus 3. Right, so remember these volumes and stuff are, that's times 10 to the fifth, this is 10 to the minus third. All right, can I do this? Okay, so I'm going to take that number that's on my calculator, multiply by 6E minus 3, multiply by 100, divide by 8E5, divide by 2E minus 3, and I get 48.07. 0.07 kelvins, right? So that's our second answer. We got our first answer. We got our second answer, right? Okay, so find the Q, delta U, and W for this process, right? Remember that these guys are related like this. Okay, and we're going to find Q by adding these two up. Okay, the work we are told is 1250, right? Okay, we know that the heat that flows in is 0. So therefore, it must, notice that the temperature dropped, right? It must be that this is negative 1250, right? Because remember, adiabatic means that the heat flow is zero, Q is zero, right? It happens quickly, okay? Isothermal happens slowly, slow, quick, okay? So the temperature drops, right? Now, we ought to be able to confirm that using this guy, right? I ought to be able to do this. Change in U is 3/2 NR change in temperature. So let's see if that works, right? 3/2, N is 1.9254, R is 8.31. Change in temperature is 100, actually it's 48.07 minus 100, right? Final minus initial is always your change, right? So let's try that. 3 divided by 2 times, I got to go way up to find, let's find that N. Where's N? Come on, baby, N. It's way up there. Oh, there it is, I found it. All right, so 3/2 N times 8.31 times parentheses 100 minus that 48 number. I'm using things that are just totally not rounded. And I get 1246.2. Right, negative 1246.2 joules, right? Notice that that's the number they gave us, right? So without doing calculus and using this, which of course is derived from calculus, right? Without doing calculus, we actually derived how much work it did, right? We can show that the internal energy drops by 1250, right? And therefore the work has to be 1250, right? Okay. I will show you how to get it from an integral of pressure times volume, change in volume, okay? But I'll do that in a separate video so that if you're just not interested, you know, you're good. You don't have to worry about it, okay?